Hi folks, today we're going to be talking about carbon cycling on Earth. And what that means is how carbon converts between different forms in different places. To review what you learned in middle school, you want to remember that we do have an atmosphere on Earth. We do have a hydrosphere, and that's all the liquid. We're talking about oceans, rivers, lakes, ponds, things like that. And we also have what's called a geosphere. That's all the minerals and rocks on Earth. Carbon exists in different forms in each of these places. In the atmosphere, you are well aware. It's in the form of CO2, carbon dioxide. Things are a little different in our oceans. The CO2 reacts with water and becomes other forms, most notably bicarbonate and carbonic acid. You do not have to memorize those forms. Just understand that CO2 does react with water to form other forms. In the geosphere, it's not the most obvious thing to see the carbon, but you can find it in rocks. Most notably, these things called carbonate rocks. The most common one that you'll find is limestone. Okay, so our amounts in each of these places differs pretty notably. In the atmosphere, we have about 800 million tons of carbon in the form of CO2. So again, that's 800 gigatons, and giga means a million tons, which sounds like a whole lot. But this is for the entire atmosphere. Now, in the hydrosphere, in the oceans and the lakes and the rivers and all of that, it's actually a significant amount greater. We're talking about 38,000 gigatons of carbon. When we get to the rocks, we're completely off the rails. We're at 100 million gigatons, so 100 million tons. And these are all rough estimates, but you can see that the atmosphere, while it is changing, and we will get to that, has very little compared to the hydrosphere, which has incredibly little compared to the geosphere. Okay, now how does the carbon move or convert between these different locations? One of the easier ones to understand is that CO2 literally will dissolve in rainwater and fall out of the clouds. This is going to lead it going from the atmosphere to the hydrosphere. And when this happens too much, you get sort of acidified rain because the CO2 becomes an acid, carbonic acid, and this has impacts on our environment. Okay, how about from the geosphere to the atmosphere? An example that you all know about in some ways is that there are certain times when the liquid magma from underneath the earth comes out along with ash and clouds of various gases, and one of those gases is CO2. So you can see that there is carbon that does move from form to form, from sphere to sphere on Earth. Now, what we haven't talked about yet is life. So we have not added in the biosphere, which is all of the living things on Earth, whether they're underground, on land, living in the air, or in the oceans. I'm going to add some of those in right now. And I'm going to put in some not so great drawings of sort of trees on land, as well as maybe those are supposed to be kelp in the oceans. Both of these are going to do a process you're familiar with, known as photosynthesis. This is going to take CO2 out of the atmosphere and the hydrosphere, depending on where they're living, and convert it into all the things we're made of. So this is, again, going to take CO2 and make glucose, but then that glucose gets converted into other carbohydrates, lipids, proteins, nucleic acids, everything that we're made of. So that's the photosynthesis aspect, both in the from atmosphere to biosphere and hydrosphere to biosphere. Do keep in mind, though, that these organisms don't just do photosynthesis, they're also doing cellular respiration, just in smaller amounts. Overall, they do way more photosynthesis than cellular respiration, but nonstop, they're always doing cellular respiration. Okay, on the right side of the diagram, I've added something that most people are not aware of, which is that certain animals actually do take carbon out of the oceans. Not by photosynthesis, but by producing things like shells. Shells, exoskeletons, and things like that are made to some extent out of carbon. So the calcium carbonate in a shell of a snail, or the exoskeleton of a sea star, or even in a coral reef, this is carbon that has been taken out of the oceans. Now, what most people don't actually know is that some of these shells and exoskeletons over time accumulate. They don't necessarily all dissolve back into the ocean. They actually become that limestone rock, which is where a lot of our geosphere's carbon is stored. So keep in mind that a lot of the carbon stores that we have are indirectly or even directly affected by life on Earth. We usually don't think of rock as being formed by life, but in this case it is indirectly coming from living things. Okay, let's look at the balance here. We haven't finished off all of the stuff because there are no animals on here or bacteria or fungi. So let's start with, say, dead leaves coming off of the trees and starting to decay, or maybe an entire dead tree, or piles of feces from animals that have been eating those tree leaves or other plants, or maybe even the animals themselves. All the animals and the things that are decomposing their feces and the things that are breaking down the dead materials on land and in the ocean are doing cellular respiration. Again, as all of these organisms, whether they're animals or the decomposers eating all the dead stuff, they're going to be breaking down those materials back into CO2 that they exhale into the atmosphere. And this is a massive amount. So all of the dead materials, all of the plants that are being consumed, return to the atmosphere, at least a significant portion of them, as CO2. Overall, this looks like there would be more CO2 going into the atmosphere than coming out of it, but that's partly because the arrows just aren't accurate. There's even fire that makes things even worse, right? This is natural fire that would add even more CO2 to the atmosphere by combustion. But photosynthesis is way stronger than it looks on my diagram. These arrows should be much bigger, and if you added all these arrows up, and if they were properly labeled with amounts, the amount of photosynthesis is enough, in general, until recently, to offset all of the cellular respiration and combustion on Earth. It should be balanced, and that's what I want you to see as being sort of what should be seen here. Okay, couple things that we haven't talked about. Turns out, not all the dead stuff actually gets broken down and respired into the atmosphere. Some of it gets buried, and some of it, if you get enough time, we're talking millions and millions of years, gets converted into fossil fuels. And this is actually a significant amount of carbon on Earth. Not a lot compared to the amount in rocks, but the oil, coal, and shale on Earth and other forms is about 5,000 gigatons of carbon. Doesn't seem a lot compared to all the limestone and other rocks, but it is pretty similar to the amount of carbon that we have in total in all of living things, in all of our carbs, lipids, proteins, and nucleic acids combined. That's how much we've got in fossil fuels. Now, the issue that we currently have is that over the last, almost 200 years, we've been taking those fossil fuels, extracting them, and then burning them. This is again called combustion, and the combustion converts these carbon forms back into CO2 into the atmosphere. And this has become an ever-increasing problem that we all have to deal with. You'll see in the atmosphere it says that it's 800 gigatons of carbon. It hasn't always been that, and it won't be that forever either. This has been changing. So I'm going to switch now. Now, I have been talking about in total amount of carbon. I'm going to switch to a different set of units. And this is parts per million. You've seen it on graphs as we've done experiments in the classroom. 180 to 280 is approximately how the range in which the CO2 levels have been on Earth in the atmosphere for the past 800,000 years. We have data, high quality data that goes back that far from boring out ice cores. And we'll talk about that later in the semester. Okay. Again, if you look at that number, ballpark around 230, give or take 50, with very few times that over the last 800,000 years that the CO2 levels have gone significantly above or below that. This is 1960. This is 1980. This is 2000. This is 2020. And as of this year, we are at approximately 425 parts per million. Again, that's a rise from an average of 230 over the last 800,000 years. This is a pretty significant difference, and we are going to talk about the impacts on our Earth that all of you are aware of in some way, shape, or form, and what we can do about it over the rest of the semester. Hope that helped you get an overview of how carbon is seen on our Earth, how it moves from place to place, and how it changes in form. Thanks. See you next time, folks.